Good afternoon, my name is Lily. I flew in yesterday from Alberta, West Canada. I'm a double-dipping student at University of Arizona and University of Illinois, Urbana-Champaign in environmental geology. And I'm currently a research assistant for Corteva Agriscience. Today, I would like to share with you a little tool that we developed to model the fate and transport of mixed agrochemical contaminants before we go out sampling as per our regulators' requests in Brazil. It's called the Chemical Conceptual Model, or CCM in short. Our site in Brazil used to be a pesticide manufacturing plant. It is located within an industrial complex where we have neighbors that had also generated their own set of pollutions. So at times we run into this problem where we have to tell apart which contaminants are theirs and which ones are ours, so that they can clean up their own mess and we can clean up ours. But here's the thing, over the years, the pumping of groundwater in our area has been constantly changing. There is already land subsidence going on in the area, and because we are quite close to the ocean, we are also seeing saltwater intrusion from the coastline. Please imagine, everybody has been doing pump and treat in this area over the last few decades. There was this episode in which we stopped pumping for just a day to do maintenance work, and our neighbor just immediately flooded. And they immediately flooded when the water table rebounded. So you can picture when these neighbors take turns in pumping and stopping, the groundwater models that we had just wouldn't ever be valid for a long time, no matter how accurate it was when we made them. Likewise, the government typically does not ask us before they drill a well and start pumping in the area to cater the growing populations downstream up north. So you can see on this map, that the latest well that they drilled was in late year 2024, and this is an artesian well that penetrates the clay layer, which separates our very contaminated aquifer from the clean one beneath the clay. So we can only pray for the government not to overpump this aquifer, because if the aquifer dries up, the clay collapses, we are pretty much done, and our stuff will be all over the place, and all our previous modeling will be rendered useless. So that will be a time in which we will more so need a tool to define our liabilities by determining which contaminants are by nature unable to travel too far from our site and which ones would have gone right away with the groundwater flow in that underlying aquifer. Currently, the regulator would ask for hundreds and thousands of samples far away from our site, and they'd keep going until the concentrations in the samples do not exceed their limits. But the problem with this is that pesticides typically have plenty of end users who would have applied similar chemicals in doses and areas beyond our control. And the fact that you found a chemical compound 10 kilometers away from us doesn't necessarily mean it is ours. So there is currently but one way to tell whether a contaminant is ours or not. It is called the isotopic analysis. It tells us the approximate age and narrows down the source locations of the atoms in a compound. But in order to do that, the lab turnaround time is about 12 weeks at University of Waterloo for a chlorine sample. And the analysis for just one boron sample is about $356 US dollars at University of Calgary, which in our view is not very affordable when it comes to thousands of samples for hundreds of compounds. So that is why we came up with this nifty CCM tool to bring down our costs by filtering out the immobile compounds so that we can save our breath from useless eternal sampling on problems that we didn't cause. So what we did was first to collect the mixture of our contaminants from our sumps. Then we replicate the soil composition of our site in a column according to our pre-existing core and auger data. Next, we centrifuged each of the soil layers with a contaminant mixture at 1,000 RPM for 1 minute to find out faster if any salts will be created, how the contaminant behaved in certain porous media. Then we poured the contaminant mixture into the soil column with overlaying clay and underlaying sand taken directly from our site. We let it sit there for 8 days, 16 days, while we drip water down onto the top to mimic natural rainfall and infiltration when the spill was still fresh. So at the end of the 16 days, we opened up the column to see which contaminants traveled all the way down to the bottom of the column and which ones were still sitting on the top, not going anywhere. To mimic a situation in which the contaminants had already been spilled for ages, we premixed the contaminants with the clay layer and dripped water down into the column. This time we let it sit there for 14 days, 28 days, and at the end of the 28 days we do the same and rank the compounds again according to their mobility. We found that 1,2-DCB was the only compound that broke through the clay in just 8 days, whereas 3CA was never ever found in the underlying sand in either the fresh or mature release soil columns. This model concludes that 3CA is the least mobile amongst the 6 compounds that we studied, and 1,2-DCB was the most mobile amongst all. So we might want to focus our sampling efforts on 1,2-DCB and take 3CA as a non-migrating plume in our risk assessment rationale. The only problems we found with this conclusion are that, number one, our model does not quite quantify how far these compounds are going to travel in real life due to a difference in pressure between the column and the subsurface. Number two, that the concentrations found in the sands are higher doesn't necessarily mean that the compound traveled downward faster. So when we compare compounds that broke through the clay after the same amount of time, we do not really know when exactly the breakthrough happened, at what speed did it travel, and in which direction each day. So the way we rank the compounds that broke through at day 16 and day 28 carries with it a lot of uncertainties, and we might want to refine our next experiments by making observations more frequently between intervals. Number three, that when we dripped water down into the column, we could no longer observe some interactions between the compounds studied and other compounds in the mixture. For example, chlorobenzenes are like a taxi for chloroanilines. When water is added to chloroanilines, they change phase and kind of disappeared from our radar. Number four, we also see a mass loss after 28 days that we are unsure whether it was due to a combination of back diffusion, volatilization, and biodegradation. Because we didn't quite heat up or cleave the soils we put in the column, the microbial activity was kept pretty much intact, which is good because it still renders our conclusion valid. But since the upward movement of the contaminants was not well understood, mobility through back diffusion and volatilization and redox and phase changes from biodegradation were out of scope of this modeling. We think the CCM would still make a helpful screening tool for the compounds that we need to sample and conduct isotopic analysis, and in so doing, we can also target more smartly the areas where we want to sample. In order to verify whether our predictions are correct, The University of Guelph happens to be sampling 2 kilometers down gradient of our site, and they are taking 3,000 samples there for the very expensive isotopic analysis. If they still find the 3Ca beyond the parameters of the plume models made by Geosyntac, but they are able to prove that the 3Ca is not ours through the isotopic analysis, it would mean that our conceptual model actually works. We asked for US EPA's verbal feedback at a previous conference, and they said they are convinced by this methodology, but they would also love to know the land use history and the lithology of the sampling site so that we can complete the narrative of a pesticide and user problem. Because if we are able to say that this is not our contaminants, the site owner of the sampling site is gonna say the same. The nice thing about our CCM is that instead of 12 weeks, we only need 28 days to finish. It saves some budget on sampling when it is targeted smartly instead of blindly. And this piece of information about compound mobility is time stable and unaffected by the forever changing groundwater flow. So the write-up for a non-migrating plume based on this rationale would be relatively easier than one that is based on concentration changes over the years. To conclude, we really are not looking into completely replacing isotopic analysis, but we think when budgets are limited and pumping keeps changing, which is a typical situation in growing towns and developing countries, the CCM will only encourage compliance and streamline reporting and regulatory efforts. So thank you so much for listening, and please let me know if you have any questions. Here's my email address, and this QR code will take you to my LinkedIn page so that we can keep in touch after the conference. Thank you.
Okay, we have time for a question. They'll get him a microphone.
Thank you. Thank you. That's very interesting. I'm part of my multiple hats. I'm a groundwater modeler, so I understand. It's very hard to model this. But with your column experiments, I'm wondering if you're dripping and you're mimicking recharge, but what happens to the horizontal component that it's the one that is usually dominating in groundwater? How do you, can you account for that? And the other is if you're using some of the sand that's on site that may have some lignite or other particles that could help with absorption that you're not able to capture in the lab, that could also, impact some of your analysis, if that makes sense.
I would like to emphasize that we are not trying to replace the other methods. We still need to rely on those to cross-check with our predictions and findings. But not all site owners have the same access to the same quality of modeling. And when the budget is limited, we are trying to limit down we're trying to limit the efforts to let our sampling efforts be smarter, so that we're still doing the plume models horizontally, but we are trying to reduce the number of samples needed to construct the plume models. So we are still doing the plume models that will handle the horizontal movement of the plume, but it's not always the case that we can afford it.